So we have seen the goal of learning in SVM. So we put the goal here again. So we maximize the margin. Okay, that means we minimize this. And we also satisfy these conditions. Okay, you remember these are the two conditions are combined into one, like this, right? So this is the final goal of SVM. Okay, so this problem is called primal form of SVM or primal problem of SVM. So that is goal. The next question is, how do we solve this problem? Okay, specifically, how do you calculate the W and B value, which minimize this and also satisfies this? So that is the goal. How do you calculate them? Okay, how to solve this problem? When we solve this SVM problem, the technique we use is called constraint optimization method, sometimes called Lagrangian multiplier method. Okay, so we're gonna use this method to solve this problem. Okay, what is constraint optimization method? I'm gonna explain it next slide and a few more. Okay. Before I do that, one of the big advantage of this constraint optimization method is the following. So you want to solve this problem using constraint optimization method. Okay, one of the advantage is if this function is convex, okay, what is convex? Don't worry about. If this thing is convex, then it is guaranteed the answer of this whole problem is guaranteed to be optimal, global optimal. Okay, so if this function is convex function and you solve this problem, then that solution is guaranteed to be the global optimum. Okay, that's big advantage of using constraint optimization method. You don't have to worry about local optima or something like that, which happens in neural net or deep learning, etc. Okay, so in SVM, if you solve this problem, okay, the solution you have is guaranteed to be the global optimal answer. You don't have any better answer. Okay, the answer you got is the best one. Okay, that's the big advantage of this using constraint optimization method. Okay. Yeah, previously I said the primal form of SVM can be solved by using constraint optimization method. So this slide explains the basic concept, very short introduction of constraint optimization method. Actually, this method, constraint optimization method, is part of optimization problem, and it's actually big area. It's part of computational learning theory. So it's a big area. So I don't want to talk about the detail here. It is definitely out of the scope of this lecture. So what is a constraint optimization method? I'm going to give you a very short, brief introduction here. So in the constraint optimization method, you first define a function you're going to minimize, okay? So you have a problem, you have your own problem to solve, then you define a function you want to minimize, okay? You define a function with a bunch of variables there and you want to minimize, that's your goal. And also there are some conditions. Some conditions are equality, some conditions are inequalities, okay? So you want to minimize this function, and also this should satisfy these conditions, okay? So these are the problems you defined. So you have your own problem, whatever it is. So then if you manage to represent your problem in such a format, okay, in such a format, then to solve this problem, you can use constraint optimization method, okay? That's the beauty. That's a very nice thing, right? So that's the definition of, that's the goal of constraint optimization, okay? And to solve it, you can use these techniques. I'm going to go over this a little later, okay? So the first thing you have to do is, first thing you have to do to use constraint optimization method, you have to define these things. You have to define this f function you want to minimize. If you want to maximize something, it's simple actually. You put minus here and minimize it, okay? So pretty much maximize, minimize is the same. So let's say minimize a function. You come up with a function, you define a function and you want to minimize, right? And then you also define some conditions, inequality or equality or inequality, okay? So you minimize this under these conditions, okay? So you define your problem like this. Then the good news is the function you define here, if this function is convex form, what is convex? Don't worry about. I'm going to explain next slide. So if this function is convex function, the good news is now you can solve this problem, okay? And furthermore, the answer you get is guaranteed to be the global optimal answer, okay? Let me say it again. So you define your problem like this, and f is convex function, then you are able to solve this problem, okay, using this technique. And most of all, the most important thing is the answer you get is the best answer, global optimal answer, okay? You cannot have better answer than the answer you get from this, okay? That's the good news. So you define it, and if the f is convex, then you are able to solve this problem, and the answer you get is the best one. It's guaranteed, okay? Okay, move on. Then how do we solve this problem? Then you want to solve this problem. The first thing you're gonna do is you define what is called Lagrangian function. Okay, the way you construct Lagrangian function is like this. So let's say you have function f, g equalities, h inequalities. Then you construct Lagrangian function j equals f function here plus every g function is multiplied by lambda constant, and every h function is multiplied by new constant, okay? So by adding all this together, this is definition of Lagrangian function, okay? So by solving this Lagrangian function, then you can solve this problem indirectly, okay? So you now focus on this Lagrangian function, okay? So how do you solve this Lagrangian function? You have some tools. These are true, okay? You take a derivative of j, okay, with respect to x, right? Take derivative of j with respect to x, okay? And then you have some other tools called KKT conditions. It says vi times hix equals 0, okay? So by using these tools, okay, these already know, you already know this, okay? So by using these tools, we are able to solve this problem, okay? We are able to solve this problem. And that answer, okay, by using these tools, we are able to answers from this Lagrangian function, and that answer is the answer of this problem, okay? That's how we solve this problem. Let me summarize this. When you a certain problem, you represent your problem in this form, okay? And if this function is convex, you are guaranteed to have a global answer, okay? How do you solve it? From this, you construct Lagrangian function like this, okay? Just plug in here, define Lagrangian function, and to solve this Lagrangian function, so now you solve the Lagrangian function, okay? Maximum value of Lagrangian function actually, okay? To get the maximum value of Lagrangian function, you use these tools, this derivative form equals 0 and this equation is 0. So using these tools, you are able to get the answer of this j. You are able to get the optimal value of x, which maximizes j, okay? So that way you can solve this problem, and that answer is same as this answer, okay? That's the basic procedure of solving this constraint optimization problem. Okay, we have seen the primal form of SVM, and now let's solve the problem using constraint optimization method. What we are doing here is basically we're going to change the primal form, primal problem, whatever you say. You're going to change it to what is called dual problem. Okay, so you change the primal problem to dual problem first, and then solve the dual problem. So then, why do you may wonder, why do you change why do you change primal problem to dual problem and solve dual problem? Okay, why not just solve a primal problem? Okay. And there are a couple of reasons. The first reason is if you solve a dual problem, actually it's much easier to solve it. And the second reason, which is more important, is that by using a dual problem, we are able to actually solve nonlinear cases. Okay. In the beginning of this chapter, I said SVM is linear classifier, but again, classifier is linear. It is toy thing, and the algorithm must have capability to handle nonlinear cases, right? So by changing this problem to dual problem, we has the capability to process nonlinear cases. Okay. We're going to talk about this dual problem a little later on. Okay, so anyway, what we're going to do here is we change primal problem to dual problem using constraint optimization method. Okay, so let's do it. So here, so this is definition of constraint optimization, right? You define function and you want to minimize it, and you have a constraint, inequality constraint like this, right? So for this function f in SVM case, we have this, right? You look at the definition of primal problem. Okay, this is the f function, and for this inequality condition, originally we have this, okay, but we have to change this to this form, okay. It says like, left hand side is less than or equal to 0. So this inequality is changed to like this, okay. So this is f and this is now h, okay. So by using this, you construct a Lagrangian form, right? J equals like this. So putting this together, we have this Lagrangian form for SVM. Okay, so this is pretty straightforward. So constraint optimization, you define f and you minimize it, right? So for f in SVM case, we have this, okay, and in optimization method, we have these conditions. For these conditions, we have this for in SVM case. Okay. So this is the way we construct Lagrangian. Okay. So you just plug in here. This one goes here. Okay. And this one goes here, H, right? So this is the final form of Lagrangian for SVM algorithm. Okay. Okay. In a previous slide, we constructed the Lagrangian function of SVM like this, right? So here the alpha is a constant and it's called a Lagrangian multiplier, and it is positive, 0 or positive. Okay, it's not negative. So when you have a Lagrangian function and you want to solve it, actually what you have to do is this. You have to maximize J with respect to alpha first, and then later on you minimize this with respect to W and B. That's what you are going to do in Lagrangian function. Okay. So our problem has changed. You remember we have the original primal problem of SVM, right? The maximizing margin, with some conditions there, right? And we modify the original primal problem into this form. Okay. Okay, good. Now the question is, the answers of this problem are exactly same as the answers of original primal problem. This question may be a little weird, but if these answers are different, then why bother, right? So these answers of these two problems should be same. So answers of this problem should be exactly same as the answers in the original primal problem, right? There's no doubt about it. Okay, it should be, right? Then how do you guarantee, okay? How do you guarantee the answers of these are same as the original answers, okay? By the way, in this area, this Lagrangian function and this dual optimization thing, all the things are called convex optimization theory, and there are a lot of material, books, lectures, etc. So if you're interested in a little detail here, you may take a look at lecture or books. There are tons of lecture materials there. Okay, this is very big research area. I don't go into detail of this thing because this a little out of the scope of this lecture. Okay, so I'm going to emphasize one thing here. Okay, so again, as I said, the answers of this problem should be exactly same as original answers, right? The answers of primal problem. Okay, so the answer to the question is the answers of this problem, okay, this Lagrangian function problem, is exactly same as original primal problem if it satisfies what is called KKT conditions. Okay, let me repeat. We have a primal problem of SVM, and we have this Lagrangian problem of SVM, okay, and these two problems have same answers. Answer is these two problems have exactly same answers if this problem satisfies KKT conditions. Okay, so if the Lagrangian function satisfies KKT conditions, then it is guaranteed that this problem generate exactly same answers with original primal problem. Okay, so this KKT condition plays a central role in this optimization problem. So we in general, I'm going to say this. In general, the answer of this one, Lagrangian function, is different from the original primal form. But if these KKT conditions are true, then the answer of this and the original primal problems are exactly same. Okay. Okay. This one is a little redundant of a previous slide. So as I said, we changed the original problem to original primal problem to dual problem first, and then we solved the dual problem. Okay, I said there are a couple of reasons. Okay, and so we construct Lagrangian function first by using constraint optimization. Okay, and the question was, okay, the answers of Lagrangian functions are identical to the answers of original primal problem. Okay, so in general here, okay, answers in primal problem is usually greater than those answers of dual problem. Okay, so these are actually, in general, they are different. The problems of primal problem actually are different from answers of dual problem in general. But there are cases where, you know, if certain conditions are met, then this original primal problem, okay, and the dual problems are identical. Okay, that means if these conditions are true, okay, then the answers of primal problem is exactly same as the answers in dual problem. Okay. So that's the importance of KKT condition here. So the KKT stands for the three persons name, the initials of three persons, okay, who first invented it. Okay. Okay. In a constraint optimization method, I said the objective function f. If that objective function f is convex, I said the solution we get from optimization, constraint optimization, is global optimal. Okay, you don't have to worry about local local optima, etc. Okay, so when you have answer that is guaranteed to be the best global optimal answer. Okay, so which is very cool. So what is convex anyway? Okay, what convex function? What is the definition of convex function? So let's take a look at this function here. We have function f. Okay, whatever it is the shape of f function. And you pick two arbitrary data, x1 and x2 here. Okay, so this is the f value of x1 here, and this is the f value of x2 here. Okay, and you draw a line between these 2 points. Okay, like this. So this formula, lambda times fx1 plus 1 minus lambda fx2, okay, this represent the data points between these 2 points, data points in this line. Okay, this data they represent here. Okay, represented as here. Okay, and this one here is any arbitrary data between x1 and x2. Okay, because the lambda is between 0 and 1, this means any random number between x1 and x2. It doesn't go beyond x1, doesn't go beyond x2. Okay, it is any arbitrary value between x1 and x2. Okay, so for any arbitrary value between x1 and x2, okay, its f value is here. F value, function value, is always less than or equal to the line value between these 2 points. Okay, that's definition of convex. Okay. So again, as I said, this convex is important because if you define an objective function in a constraint optimization method, and if that function is convex, then basically you are all set. You are guaranteed to find the global best answer. Okay. Okay, in this slide, we show some example of convex function. So if you look at this picture here, this is example of convex. So as I said in previous slide, you pick two random points like this, and you draw a line here. Then, as you can see, this line is always greater than, okay, the value of f, right? So this line, the values in this line always greater than this f value. Same thing, you pick these two data, okay, and then data in this line is always greater than the f value here, right? So this is convex. The opposite of convex is called concave. Okay, this is concave. But actually, concave and convex is the same, because the only difference is their the sign. If you put minus in in front of objective function, let's say minus f, then it becomes concave. So basically, concave, convex is pretty much the same. Okay, the only difference is their direction, their sign. Okay. So in concave, if you you select 2 point here, and every data in this line is lower, okay, lower than the f value, okay. So convex concave is pretty much same. The only difference is their direction, okay, their sign. This one here is, let's say we have a function like this. This is not a convex because you draw a 2 line here. Then you see this line. In this case, this looks like okay, convex line. The line is above the f curve, but in this case, this line is under the curve, so it is not convex, and this is not concave either. So this is not convex. This is not convex either. It's just no. So in this case, if you define objective function to use constraint optimization method, and that objective function turns out to be convex or concave, and basically you are lucky, you are done. Basically, you can solve the problem, and the answer you have is guaranteed to be the optimal, grand optimal. Okay, but if the objective function you come up with is here, it's not concave, is not convex, then the answer, yes, you can get the answer by using a constraint optimization method, but the answer is not guaranteed to be a global optimal. Okay, that answer can be a local optimum, right? So that's convex. Okay. So try to define a certain a category of convex function when you define objective function. Okay, this is another example of advanced stuff. This is about Hinge loss. We studied the loss function a little bit in neural net. We talked about cross entropy and KL divergence, etc. Okay, and this is another example of loss function. It's called Hinge loss. And the reason I talk about Hinge loss here in SVM is when you look at some other SVM textbook or other lecture or whatever, okay, if you look at this formula, this is the Lagrangian form of SVM. We have seen this many times, right, in previous slide as well. Okay, so in this Lagrangian form of SVM, sometimes this part is replaced by this, okay? In some other cases, some other text or some other SVM method, okay, this is replaced by this, okay? And this is called hinge loss, okay? So here in this chapter, we don't use hinge loss, okay, we use this one, okay? But some other case, in other SVM algorithm, sometimes they use this, okay? So don't be mistaken, okay? These are pretty much very similar. Especially when you use a soft margin SVM, which you covered later on, most likely people use this one instead of this, okay? So, yeah, sometimes we use this and sometimes we use this, okay? So again, in this chapter, we want to use this one, okay? Anyway, it's hinge loss. What is hinge loss? Hinge loss is definition is this, okay? Hinge loss is maximum value between 0 and 1 minus y fx, okay? So y means the true value, okay, and fx is the predicted value, right? So simply put, we can say this like if prediction is correct, okay, the prediction of algorithm is correct, this loss is 0, and prediction is incorrect, then it returns this value, okay? So that's how this hinge loss works. So let me go over a little in detail here, okay? For example, let's say y true value is 1, okay? Y true value is either 1 or minus 1, okay? It's binary. So suppose y is 1, okay? And then if prediction is correct, that means fx value should be greater than 1 or equal to 1, right? So this value should be 1 or greater than 1, right? This is 1 and this is 1 or greater than 1, right? So that means 1 minus y fx, okay, is minus, right? Let me repeat this. Suppose y equals 1 and f then, prediction is correct, I said. If prediction is correct, fx is greater than 1 or equal to 1, okay? So that makes this part negative, right? So this is negative. The prediction is correct. This part is negative. So hinge loss chooses maximum between 0 and this is negative if prediction is correct, so it returns 0, okay? So that's why if prediction is correct, hinge loss returns 0. And okay, and then if prediction is incorrect, okay, then let's take a look. Let's say y equals 1 again, okay, and then if prediction is incorrect, then that means fx value is less than minus 1, okay? That's from the definition of SVM. Its true value is 1, and if prediction is incorrect, the fx should be less than minus 1, right? You remember the definition of SVM, the line to a line there, okay? So this is 1, this is less than minus 1, okay? So this is minus, there's another minus here. So this whole thing is greater than 2, right? So this whole thing is greater than 2. So this is maximum between 0 and something greater than 2, right? So it returns this, a positive number, okay? So in summary, if you use hinge loss, if prediction is correct, okay, the prediction f here, if prediction is correct, it returns 0, loss is 0. If prediction is incorrect, it returns a certain positive number, okay? It can grow, it can be very big number, okay? So the purpose of using hinge loss is like this. If you use hinge loss and then if your prediction is correct, it gives no penalty, okay? Loss is 0, okay? And on the other hand, if your prediction is incorrect, it gives a lot of penalty. Okay, so that's how the Hinge loss works. So if you look at this picture here, okay, so if yfx, this is value of yfx. So if the prediction is correct, this means 0. Okay, it returns 0. And if it returns incorrect, this error grows linearly. Okay, so it can be any number. Okay, 1, 2, 3, 4, 5, whatever. Okay, so that's how the Hinge loss works. Okay, so sometimes mostly we use this. Sometimes we use this. This is replaced by this, especially in soft margin SVM. So that's Hinge loss. One of the problem of Hinge loss is, as you can see here, this is not differentiable. So that's problem. This is Lagrangian function. Okay, you're gonna differentiate this later on. Okay, but if you use Hinge loss function, Hinge loss here, you can see this is Hinge loss graph here. It's not differentiable, right? So if you use Hinge loss here, then the Lagrangian function is not differentiable. So we have a problem. Okay. So if you use Hinge loss function, you have to use a certain a special technique called a self-derivative or self-gradient, whatever you call it. You can use this. You have to use this special technique to differentiate this Lagrangian function. Okay. Okay. So far we have seen pretty much everything about the theoretical background of SVM. That includes the primal problem of SVM, the maximizing margin with some conditions, okay. And we also said we're gonna change that problem is called a primal problem. And I also said we're gonna change the primal problem to dual problem. Okay, by using a constraint optimization method. Okay, and if in constraint optimization method, if the objective function is convex, then we are guaranteed to have the optimal answer. Okay, and actually that's the best advantage of SVM. That's the strength of SVM actually. Okay. And also we talked about KKT conditions. Okay, that is so we changed the primal problem to dual problems. Okay, the question is, are these two problems identical? That means the answers from primal problem is exactly same as the answers from dual problem. Okay, that's the question, and the answer to the question is, if the problem satisfies KKT conditions, then those two problems are identical. Okay, that means their answers are same. Okay, so the KKT condition is important in changing primal to a dual problem. Okay, so if KKT is true, the dual problem, primal problem has same answer. Okay. Okay, that's pretty much about the theoretical background of SVM. Okay, so now let's solve it. Okay, solve it means let's change to a dual problem. Okay, using KKT conditions. Okay. So this is the original. This is Lagrangian form of SVM. We have seen many times. Okay. So we use KKT conditions. These are KKT conditions, okay, and you take derivative of J with respect to W, and we have this, okay, and we take derivative of J with respect to B, and which is this, okay, and we have another KKT condition saying this, okay. Actually, here in this says either alpha or this is 0. Okay, usually, either this or this is 0. Okay. Anyway, by using KKT, we have this condition, this equation, and this equation. Okay. So by using this, you're gonna paraphrase this formula, okay? And that becomes dual problem. Okay, this formula here is the Lagrangian formula. Basically, we expand it. Okay, expand means we remove the parentheses. Okay, so that's how we got this one. Okay, and we're gonna change this to dual problem. Okay, by using the conditions I mentioned in the previous slide. Okay, the three the equations. By using those equations, you're gonna transform this to dual problem. Okay. So for example, you have this condition, so it's going to be like this, and this slide is very easy to follow. Okay, you just each term is replaced by this. For example, this one here, W transpose W is replaced by this because of this, and this one here is replaced by this. Okay, it is actually same. Okay, because of this, and this is actually 0. Okay, because of this, etc. So you plug this in here and rearrange it. Okay. So by plugging in all these equations and rearrange those terms, now we have this final formula here. Okay, and this is called dual problem. Okay, and by the way, we changed notation from J to Q because we don't have WB anymore. We have only one set of variable alpha. Okay, so you change notation to Q alpha. Okay, so this is a dual problem. We have only one set of variable alpha. Okay, and it's called dual problem. So finally, in dual problem, what we're gonna do is we're gonna calculate this alpha value. Okay, and which maximize this. Okay, we get alpha which maximize this. Okay, and that's the final the value of alpha. If you know the value of alpha, you can determine the W or B, the line. Okay, you can calculate them very easily. Okay. So this is the final form of dual problem. Okay, so we maximize. Now we maximize. Okay, we maximize Q like this. Okay, subject to this. Okay. So we changed primal problem to this dual problem. Okay. So if you remember, in the beginning I said when you solve SPM problem, we define the primal problem first, and then we change it to a dual problem. Okay. So why do we change original primal problem to dual problem? Okay. And there are a couple of reasons. Okay, the first reason is, as you can see here, we have only one set of variable alpha. Okay, and this is quadratic form, so it's very easy to compute. Okay, the problem is much easy. On the other hand, if you look at the primal problem, we have inequalities, and you have it's very problem is very very cumbersome, very inconvenient. Okay, it's very difficult to solve it. Okay, so the first reason of changing to a dual problem is this dual problem is easier to solve it. Okay. Second reason is actually this second reason is much more important. Okay, is this dual form contains this term. Okay, xi transpose xj. Okay, this is super important. Okay, we changed primal problem to dual problem mainly because of this term. Okay, dual problem contains this. Okay, then why do we? You may wonder why this thing is so important. Okay, right? Why this thing is so important? Okay, We're going to talk about it, okay, a little later on, okay, but I'm going to say here is, this, because of this term, we are able to solve non-linear problem, okay? That's why this thing is super important, okay? So this is dual problem, okay? So you solve this problem. This is dual quadratic problem. This is a very easy problem. And when you get the alpha value, the W value can be calculated very easily, like using this, okay? Okay, this slide shows some advantages of solving dual problem instead of primal problems, okay? As I said many times, we change primal problem to dual problem and solve dual problem, okay? There are many advantages to it, okay? So the first reason is in dual problem, we have only one set of variable alpha instead of WB, okay? So its problem is much easier. And also in dual problem, the problem is, whole problem is quadratic problem in terms of alpha, which is another very simple problem, okay? Third reason is many of the alpha are actually zero, okay? Actually in SVM, only a couple of only a couple of alpha are not zero, okay? Most of alpha are zero, and just a few, like 2 or 3, 4, at most 4 alpha are not zero, okay? So this makes our computation very, very easy, okay? Very fast, very easy, okay? So alpha value are very, very sparse, okay? When it comes to constraint, in primal problem, the constraints are inequality, which is very difficult to handle, okay? But in dual problem, the constraint is now equality, okay? So it's much easier to handle. And finally, and the most important advantage is in dual problem, we have this term, okay? We can represent dual problem with this term, okay? Xi transpose Xj, okay? And this is the most important reason of using dual problem, okay? This is the basis for nonlinear SVM. Because of this, we are able to process nonlinear problems, okay? So by solving the dual problem, solving dual problem means you get the values of alpha, okay? That's the solution of a dual problem, okay? So once you solve the dual problems, you get the values of alpha, okay? And actually, most of the alpha actually zero, as I told you in previous slide, okay? There are, for each data in SVM, for each data we have one alpha value, okay? So we have, let's say we have 100 data, that we have 100 alpha, okay? One data, one alpha value, okay? So, but what happened is majority of alpha are actually zero, okay? Just a few, I think at most four alpha are not zero, and for the rest alpha, the values are zero, okay? That's what happens in SVM. And so let's say there are some data Xi with non-zero alpha. I said for most of data, the alpha is zero, okay? But there are some data with non-zero alpha, okay? And these data are called support vectors, okay? And these support vectors are actually the data that determines the linear line of SVM, okay? And decision boundary is actually determined by these support vectors, okay? So once you get the value of alpha, the direction of line W is determined by this, okay? Alpha is here, Y is the Y value, class value, x is the input x value, etc. Okay, so you can get w value here, right? And when you make classification, okay, this is line. Okay, so using this line, you can make classification. Okay, so if this value is greater than 1, it's here. Okay, if the sum is positive, it means class is 1, or it's a negative, it says the class is 0 or minus or whatever. Okay. So this picture shows the examples of the alpha. As you can see here, there are many data, okay, and for each data they have alpha value, okay, and you see, for all this data, the alpha value is 0, 0, 0, 0, 0, 0, 0, okay. This one, alpha is 1.4. This one, alpha is 0.6, alpha is 0.8, okay. For these three, the alpha value is not 0, okay. For the rest, the alpha value is 0, okay. So as I said, the alpha value, majority of alpha value is 0, okay. Just a few, in this case 3, just a few data has, non-zero alpha value, okay. And these 3 data here, these 3 are called support vectors, and the final line, SVM line, is determined by these support vector only, okay. All the other data has nothing to do with this line, in determining this line, okay. Only these 3 data, called the support vectors, determine the actual line of SVM, okay. These 3 data is what really matters in deciding the line, okay. So this one here is the summary of we have seen so far, okay. And so this one is the primal problem, okay. So we maximize margin here, and we have some conditions, okay. Remember, there are 2 lines, okay. So this is a primal problem, or say primal form, whatever you say, okay. And we change this to this dual problem. This is called dual problem, okay. So when you change it, we use Lagrangian multiplier, also known as the constraint optimization method. Those are 2 the same thing actually, okay. So by using a Lagrangian multiplier or constraint optimization, you change primal to dual problem, okay. And also I mentioned that when you actually the answers of this problem, answers of primal problem and answers of dual problem may be different, okay. Actually, in general, these are different, okay. But there are some cases, some conditions where these 2 problems are identical, okay. And that conditions are called KKT conditions, okay. So if this problem satisfies KKT conditions, then these 2 problems are identical, okay. So when you change these to this, primal to dual, we use KKT conditions, okay, to change primal to dual, okay. Okay, once you solve the dual problem, now you get the values of alpha, okay. Then by using the values of alpha, now you can calculate the W value and the V value, okay, by using this formula, okay. So this is the final line of SVM, okay. W comes here, and V is this, okay. This is the final line, okay. So when you classify, when you have new data, you're going to classify with using SVM. You use this function, this linear function, okay. And if this value is positive, then it's class 1, and this value is negative, then the class is the other one, okay. So that's how it works. Okay, we're going to see a small example of linear SVM, okay. So let's say we have data with 2 attribute, x1, x2, and the y is the class value, okay? And suppose we calculated alpha value, okay, using dual problem, okay, that process is not mentioned here, okay, it's skipped. So let's say these represent the alpha value of each data, okay? This one row means one data, okay? And for these two, their alpha value is not 0. For the rest here, their alpha is 0, okay? As I said, most of data, their corresponding alpha is 0, okay? So this picture shows the line of SVM, okay? So in this case, these two data is support vector, okay? For these two, their alpha value is this, okay? This. And for the rest, their alpha value is 0, 0, 0, 0, 0, 0, okay? So that's how it works. So this is the line, right? And okay, this slide shows how we get the W value and the B value in previous slide, okay, by using alpha. Okay, so by this definition of calculating W, okay, so from this, actually in previous slide, there are only two data with non-zero alpha, okay, so we're going to use those two data only, okay. For the rest, the alpha is 0, so you don't have to worry about, okay. So for W1, we consider the first attribute, okay, so this is the alpha of the first data, this is alpha value of second data, and this one here is the class value of first data, okay, this is the class value of second data, and this is the value of first attribute of first data, okay. This one here is the first attribute of second data, okay. Again, same thing, the alpha of first data, alpha of second data, class value of first data, class value of second data. This one here is value of second attribute of first data. This one here is the second attribute. I'm sorry. This one here is second attribute of first data. This one here is second attribute of second data. Okay. So this one here, all these things use first attribute. Here we use second attribute. Okay. So how you do mathematics here, you do this number. And B1 is using this, okay, by definition, you plug these number values here, okay, and we have this. So that's why we have this W value and B1 in previous slide, okay. Now we talk about the soft margin SVM. Okay, soft margin classifications. Okay, in linear SVM, okay, we calculate the line, okay, and that is a strict line. Okay, strict line means, so let's say we have line here, okay, and everything in this side should have same class, whatever it is, okay. And every data in this side should have same class, okay? No exception, okay? That's the definition of linear SVM, okay? So there is no error, okay? And that's a linear classifier, okay? Linear SVM actually. So here, what you're gonna do is called a soft margin SVM, and what you're gonna do is actually we're gonna allow a little bit of error, okay. So if you look at this example here, okay, we have a SVM line here, and also we have two parallel lines, and we have this support vectors, okay, the same old story, okay. And what is different here is, if you look at this data, okay, this data is blue, okay, it is supposed to be here, okay. And again, look at this red data here, and this red data is supposed to be here in this side, right? So this is error. If you draw this line, this is error, and this is error, right? So the basic idea of soft margin SVM is we are looking for line, but at the same time, we allow a little bit of error, okay? This is not strict line, and this is a line, but we allow a little bit of error, okay? So in this case, for these two data, for this data, this one is error, okay? If you use this line, this is error, right? This data is error. And this one here is Chi1, okay? This Chi1 is the size of error, right? So this data is error, and this is the size of error. Chi1 is size of error for this data, okay? And for this data, again, this is data is error, okay? And this Chi is the size of error for this data, right? So this is pretty much same as the linear SVM, but we allow a little bit of error, okay? And that is called soft margin SVM, okay? So the reason we need a soft margin SVM is, so if you look at this example, if you wanna draw a strict line, it's impossible, right? You cannot find a linear line which separate this, right? So the boundary should be something like this, right? Non-linear, okay? So if you want to use line, you definitely have some error there, and you have to allow a little bit of error, and that soft margin SVM, okay? Okay, this slide is kind of redundant to the previous slide. Okay, so again, we are using a soft margin SVM. Okay, that means we allow a little bit of error. Okay, so if you look at this example here, and we draw a line here. Okay, and these three are support vectors, right? So using these support vectors, we come up with this line, okay, which is this, okay. So if you draw a line here, then we have some error, okay. This xi is definitely error. This, using this line, this data should be somewhere here, right? So this is error, and the size of error is psi I here, okay. For this data, size of data, the error is psi I here, okay. This is size of error, okay. And for this data should be here, okay. This data is the same side as the other guys here, okay. But still, this guy should be above this line. So this guy is error too, and size of error is psi j, okay. This one. This is the size of error for this data, okay. So if you draw this line using these support vectors, okay, then we have two errors, and for this data, these are their error, size of error here and size of error. So we allow a little bit of error, and still we draw a line, okay. So that's soft margin SVM. Before I move on, you may wonder, okay, then what if we draw a line with something like this, okay? Something like this, okay, then we have no error, right? We have no error, okay. Yeah, we have no error for this data. For this training data, we have no error. But if you draw a line like this, its margin is super narrow, okay? Very, very narrow, right? And that's no good. In SVM, we prefer a line with maximum margin, okay? Maximum, the wider the better. And so this line, this margin is pretty big, okay, which is good. We draw a line here, it's narrow, margin is super narrow, okay. So it's overfitting pretty much later on, okay, so we don't like it. So instead of drawing line like this, we draw line here, and then so if you have large margin here and allow a little bit of error, so that this is much better than drawing line like this. Okay, that's the advantage of using softmax margin. So soft margin SVM is very similar to the linear SVM. Okay, just a few differences. So if you look at this definition here, this is definition of soft margin SVM. So the similarity between linear SVM and soft margin is they both maximize margin. Okay, that is the common thing, and there's some difference here. Okay, we look at this. This is the conditions of soft margin SVM. Okay, so here this means every data. Okay, if class value is 1. Okay, class value is 1. Its value should be above this line, right? To remember. Okay, so in a linear SVM, our class value 1 should be above this line. Okay, but here in the soft margin, this one here says we allow a little bit of error. Okay, this is size of error. Okay, same thing here. If class value is -1, the data should be less than below this line. Okay, below this line. And also same thing in soft margin, we allow a little bit of error here. Okay, right? So that's the only difference. Okay, the rest is same, and the maximizing margin is same, and but in condition we allow a little bit of error like this. Okay, so that's the only difference. Okay, yeah, of course this xi should be positive. Okay, it does, otherwise it doesn't make sense here. Okay, so it is positive, and this xi variable is the size of error for each data. It's called a select variable. Okay, so for every data, if the xi is 0 for every data, this whole problem is now becomes linear SVM. Okay, because there is no error. Okay. Okay. Yeah, as we have done in linear SVM, let's take a look at the primal problem of soft margin SVM first. Okay, and then we're going to change this to dual problem as well, just like we did in linear SVM. Okay, so in soft margin SVM, okay, basically we maximize the margin. Yeah, just like we did in linear SVM, we maximize margin. And also there are some errors, right? But we're gonna minimize the error. Okay, so we have two goals. We maximize the margin of line, and also at the same time we're gonna minimize the total error. Okay, it makes sense. Okay, that's the goal of soft margin. In linear margin, we don't have this minimize error as something like this. We don't have this, okay, but because there is no error. But in soft margin, we allow some error, but we're gonna minimize it, right? So in soft margin SVM, we're gonna maximize the margin, and also at the same time, we're gonna minimize the total error, okay? So let's represent this thing in a formula, and which is this. So we minimize this. This one is familiar, okay? As I think by now you guys know what this is. So this means we maximize the margin, right? If you don't know what this means, you go back to the linear SVM and take a look at this why this thing is about maximizing margin. Okay, so this is about maximizing margin. And this C is constant, okay, and this is summation of error, okay. So we minimize two things, okay. You minimize this and this, okay. So minimize this means we maximize margin, and we minimize this means we minimize total error, right? C is constant, it's trade-off between these two, okay. So in soft margin SVM, the objective function f is this, okay? this one here, without this one here is the objective function of linear SVM, okay? In soft margin SVM, we have another term of this, okay? This represents the summation of error, okay? So we minimize two things simultaneously, okay? C is a constant. It's trade-off between error and the margin, okay? You want to emphasize this. You will increase the value of C. You want to emphasize the margin of line. You reduce the value of C, okay? So this is trade-off between these two, okay? So finally, the primal problem of soft margin is as follows, okay? So we minimize this as I've seen here, okay? This might minimize this, and you subject to this, okay? This was mentioned in previous slide, and the conditions are combined into one line, okay? So this is the primal problem of soft margin SVM. The only difference, okay, the only difference between this and the primal problem of linear SVM is in soft margin SVM, we have this and this, okay? In linear SVM, we don't have this and we don't have this, okay? So without the terms of the red circle here, this is primal problem over linear SVM. With this red circle terms here, that is primal problem of soft margin SVM, okay? So we defined the problem of soft margin SVM, okay? And just like we did in linear SVM, we changed this to dual problem of soft margin SVM. So the idea is same. We use Lagrangian method, okay, and the KKT condition, etc. Just pretty much same, okay. A couple of different here is, as I said in Hinge Loss, okay, when people use the soft margin SVM, they use Hinge Loss, okay, and it's for objective function. And because they use Hinge Loss, when they take derivative of the objective Lagrangian function, they use what is called self-derivative or self-gradient method, okay? And so that's the only difference, and the rest is exactly same, okay? I don't go over the self-derivative method. This method is to calculate derivative of of non-differentiable case, okay? So anyway. So by using this, we can change the primal problem to dual problem like this, okay? So this is dual problem of soft margin SVM. So as you can see here, the dual problem of soft margin is very similar to the dual problem of linear SVM, okay? The only difference we have is this part. Okay, for every alpha, okay, its value is limited to C. Okay, for every value alpha, its value is less than or equal to C, is limited to C. That's the only difference, okay? There's only difference between the dual problem of SVM, soft margin SVM and linear SVM, okay? Yeah, and we solve this problem, quadratic problem, okay, and we get the values of alpha, okay, then we are done, okay? Okay, this is a summary of soft margin SVM, and this one here is actually the primal problem of linear SVM, okay, and so in soft margin SVM, we allow a little bit of error, right, xi. So by allowing some error, and this is the primal problem of soft margin SVM, okay. So the only difference here is we have this term, okay, the summation of error, and C is the constant, okay, and this condition is changed like this, okay. So for each data we allow a little bit of error, okay. So these two are differences, right, and the rest is exactly same. So this is primal problem of soft margin SVM, okay. Again, C here is the constant, and it it's kind of how much weight you're gonna give to this error, or how much give weight to this margin, okay. You think the maximum margin is very important, then you give very small value of C, and if or this reducing error is very, very important, then you increase the value of C, okay. So it's that's parameter C that determines, okay, the weight balance between these two, okay. And also, as we did in linear SVM, we changed the primal problem to the dual problem of max margin SVM, and this one here shows the dual problem of soft margin SVM, okay. So again, it's pretty much same except this one here, okay. So every alpha in soft margin SVM is alpha value is limited to C. Then that's the only difference, okay. The rest is identical to the linear SVM, okay. So using this by using this formula, you get the values of alpha, okay. So then you have W value and B value, okay. So this is the final line SVM classifier in soft margin SVM, okay.